the people inside the Zoom to ask you during the presentation?
Yeah, sure, no problem.
All right. Okay, and then please don't forget to record your attendance. So the attendance link can be found in the chat box area. Okay, Alhamdulillah, we are honored today to have Assistant Professor Dr. Izzuddin Tamrin to give a talk on potential of artificial intelligence in healthcare, examples from our research project for the KICT Intellectual Talk Series. First of all, let me share a brief profile of our speaker. Dr. Izzuddin Tamrin is an assistant professor at the College of Information and Communication Technology, teaching database systems, database programming, information retrieval technologies, data communications, and e-commerce. He is a member in Smart Data Analytics KICT Research Unit. His research interest is machine learning, information system, and computing. All right, so without further ado, I would like to invite Assistant Professor Dr. Izzuddin Tamrin to start the session. Please welcome.
Okay, thank you very much, Dr. Rafiez. Assalamualaikum warahmatullahi wabarakatuh. Bismillahirrahmanirrahim. I hope everybody can see the screen and also can hear me. I hope. Okay, so before I start, thank you very much to Dr. Azura from Head of Research Office inviting me for this sharing session, KICT Intellectual Talk Series for today, 17th of December. So my topic for today, okay, is the potential of artificial intelligence in the healthcare, example from our research project. So we try to take some example to show you all the potential of this AI. Okay, let's move on. Okay, a bit of a background. Basically, okay, let me see whether I can. Now I can see. Okay, this artificial intelligence was coined during the workshop that led by Professor John McCarthy from Dartmouth College. And then in summer of 1956, it was done in Dartmouth College. And then it was like a crowd of mathematicians and also computer scientists, all the prominent one. For example, there Marvin Minsky from MIT, Rochester from IBM, and Claude Shannon from Bell Laboratories. During this huge workshop, so they wanted to come up with a system that are intelligent, that can simulate the human intelligence. So this come with the birth of Symbolic Ai. So this was the first AI that we have during this time. So basically, it represents knowledge with a set of rules. So you can, it's similar to the expert system. So you can use logic to manipulate this knowledge. The application of this is medical diagnostic. So basically, you can diagnose symptoms, disease through the symptoms, and then come up with a tentative diagnosis. So basically, this was the background. Okay, more on of background. After that, we have a different camp. We call them the connectionist camp. Okay, so basically, they use a different approach to AI, artificial intelligence. So basically, they are inspired by the brain, how the brain functions. So it was in 1958. So basically, 2 years later, it was led by Frank Rosenblatt. So basically, Frank is actually what I can say is a PhD student in Cornell University, specifically the Aeronautical Lab. So he was funded by the Navy, US Navy, to come out with a system that can recognize objects. So he come up with a perceptron, so neurons that simulate how the brain works. So basically, he had created one device with 400 light sensors for that sensors, some kind of sensors, so that it can take a picture. Okay, and then from the light sensor, take a picture, and then do some computation to figure out what kind of object it is. So it involved 1,000 neurons. Okay, so after a while, because the result was not promising, it was not it was not as expected. The hype was not, there was a hype, but it was not, the result was not as what they hoped for. So basically, the first AI winter was in 1970. All the government funding was dried up. However, there's Geoffrey Hinton in 1988 wanted to revive this AI, especially with the connectionist camp from University of Toronto, and then one of his colleagues from AT&T Bell Lab, Yan Lee Kun, wanted to come up with a instead of using a very specialized machineries that are expensive, so they just use cheap computers. So basically, through that, because of that, it's possible for them to come up with a optical character recognition system that was used by almost all the banking institution before this to automate the checking process. So basically, his team, Geoffrey Hinton, won the Turing Award. It was like a Nobel Award, but for computer scientists. Okay, so because of this successful development, so basically the AI movement was again on the right pace. However, the problem is that especially the neural network that imitate the brains, it use a lot of data crunch. It will need a lot of data to have a very high accuracy. So during that time, it's very difficult to get a huge amount of data for training purposes. However, as the years move on, so we have now a smartphone. So in Web 2.0, instead of a static web where you have in Web 1.0, so Web 2.0, basically people are, having their own contents through smartphone and social media. So now we have a lot of data that we can train for a lot of purposes. Then NVIDIA, created a very generic platform. Before this, the GPU was used to manipulate 3D images. But now, they have introduced CUDA, Computer Unified Device Architecture. Basically, it can be used for a more general purpose, and of course, it can be used for training of the neural network. So a lot of people now are using GPUs to train their data because there's a lot of data involved. Okay, with this development, so basically, remember Prof. Geoffrey Hinton, he has a PhD student called Alex Krzyzewski. So basically, he exploited this GPU with the CUDA platform that are available by NVIDIA. So he entered a competition called ImageNet. So it was in 2012. Okay, so basically, he was able to classify 1 million images. So there's a lot of images, right, in this competition. So basically, everybody have the same data set. And then we wanted to see, who can develop or design an architecture. For Alex, it was called AlexNet with 11 layers and 650,000 neurons. So basically, with the ability of the GPU, it can crunch all the data, do the training, and the error rate was only 15%. That was remarkable at that time. So basically, he won this particular competition. But the competition go on until I think 2017. And then it was stopped because it have reached the error reached low than 5%. So basically, it's like better than human when we human decision. So basically, that's why it was stopped at that time. So if you look at this particular graph, so during 2010 until 2015, the architecture involve a lot more layers. So when you have a lot more layers for your deep learning, so you will have a better error rate. So you will reduce the error rate. So the human level performance is only 5%. But if you look in 2015, we have a ResNet, they call it residual neural network that achieved 3.57%. So it was better. However, the number of layers exploded. The year before this, it was only 22 layers, but in 2015, it was 152 layers. Other than that, Google created GoogleNet for 2000 ImageNet competition for 2015. The layer was only 22. So Google created based on the architecture from Likan, the one that we have mentioned just now, that worked with that Professor Geoffrey. Okay, so some of the introduction before we move on to our project. So just a brief background, okay, on what is deep learning. So basically, it tried to simulate the human brain. So basically, we have these neurons, and then this neuron will be connected whenever we see some image. Only those important connection will be activated so that we can recognize the features of the image, and then we can deduce, we can classify it as a cat maybe. For example, if we see a image with a image or an object with the ear is a long ear, okay, and then they have like some kind of missile, you know, what you call that. Okay, and then you can some part of your brain will be activated, and you will classify it as a cat. So basically, the input, okay, or the images will be so for each neuron, how we will be how do we simulate in our deep learning? So basically, it's just a summation of the weight connection with all the inputs that we have from the other layer or from the first image that we have, and then we're going to forward feed it until we deduce, until we can classify what are the objects that we are seeing. Of course, for each one of them, for each one of these neuron, we will have to go through an activation function so that we can model a non-linear. So basically, a non-linear model. So it's very important, especially when the objects is getting more complex. Okay, some of the activation functions that are very popular are ReLU, TANT, and also sigmoid. Okay, so basically this is how a normal artificial neural network or deep learning. Deep learning, the difference between deep learning and artificial neural network is just that deep learning have more layers than neural network. Basically, it's the same thing. Okay, so we have an input layer. So for example, here we have an image of number 3. So basically, we're just going to transform it into a one D tensor, okay, or just one metric, and then it will be calculated as it moves to the hidden layer. It will be calculated as what we have shown in the previous slide. So it's just summation of all the inputs times the weight, okay, and then it will be activated with the activation function, and then it move until the output layer, and then it will recognize based on the activation. So if you look at this particular figure over here, all of those neuron with the darker tone. So basically, those are the connection that are activated, okay, and then it will lead to the classification of number 3. So that's how basically deep learning neural network works. Okay, so what happened if you get it wrong, right? So let's say through this picture here, image number 3, and then the deep learning network is going to categorize it, okay, as number 5 instead of number 3. So we need to do some adjustment, okay, on the weightage, weight connection between all of these layers, so that we boost up, okay, so that the connection for categorization for number 3 will be more relevant. So basically, if you look here, okay, for number 3, I don't know whether you can see my cursor that I'm moving. So we need to boost up all the weight for the output for number 3. So that's why you see in the second hidden layer. So where the most important neuron, okay, that will activate for the categorization of number 3, all the weight will be increased. However, if you see for first hidden layer, all the weightage will be reduced. Why? Because that will not contribute to the activation of to be classified as number 3. So that's why it has been reduced. So if you have any question, you can just ask me, no problem. Okay, so having known, okay, the background of what is deep learning, right, the network. So basically, we will introduce our project. So it's easier for us to understand if we have the basics. So the first project is called supervised retinal vessel segmentation. So these are very important. We need to automate. So basically, we take a picture of this retina. If you see the picture on the left, so that is our retina. So when we take a picture, it's not clearly visible the structure of the vessel. So why is it important for us to structure the vessel? Is for the eye specialist to diagnose whether we have some kind of a retinal disease. So we wanted to automate this process. So basically, what our deep learning will do is that if it is a vessel, we will color it as white. If it is a non-vessel, we will just color it as black. So the result will be on the right picture, if you can see that. So that is the structure of our vessels, retinal vessels. So this is what we are trying to do. Okay, for any neural network, the most important thing is to extract good features. So we have to decide what kind of features that will discriminate so that we can distinguish between the retinovascular and also the background. So there must be some kind of a contrast. Okay, so what we wanted to do is just to convert the original image, our retina image, into these color spaces. So this will be our new features. Why are we doing this? The motivation is that so that we will have is to perceive the image as how human will perceive it. So these are some of the color spaces that we have used. And then based on the result, I think we did greatly here, I think. Okay, so we transformed it into RGB, XYZ, LAB, okay, and then we use some of the existing algorithm that is already there, like multi-scale vessel enhancement by Frangis. And then at the end, we get 21 number of features that we can use to fit into our neural network. Okay, so this is our neural network. These are the configuration. So what is the purpose again? It's just to learn how to recognize the pixel, whether it's a vessel or non-vessel. Okay, so basically we have 10 hidden layers, if you have seen just now, right? So we have 2 hidden layers in the middle. And then these features, 21 features, we will get it after we have made some transformation with the original image. Using the color spaces. So we have 21 features. Okay, and then the output, we just classify it using a hard classification. 0.5 is, so it means that yeah, if it is a vessel, it will be more than 0.5. It is non-vessel, it will be less than 0.5 according to the probability. Okay, so what are where did we get our image from? So we have gotten it from 2 different sources. So one is the public data set we call that are called Drive. These are very popular data set, digital retinal images for vessel extraction. So basically they have 40 images over there. So 20 of them will be used for training, and then 20 will be used for testing. Okay, and then the other one, we got it from IUM actually, optometry imaging data set. So we have gathered 195 images. So 98 will be used for training and 97 will be used for testing. So basically we just combine drive and IUM automatically together. So this is the configuration. So in terms of result, if we can see the accuracy of our method compared with others methods out there is not quite bad. It's okay. Okay, at least it's like the top 3-4, right? It's okay. Okay, so according to the ROC curve, ROC curve, so basically is 0.96. Is I think quite high. I think it's the highest among the rest of the other methods. So our hyperparameter I think is quite optimized. Okay, so what is the meaning that we get when we assess the result from our deep learning? So basically, if you look at this particular graph, as the year increases, the sensitivity will decrease. So what do we mean by sensitivity, right? So it will measure, okay, the ability of our deep learning to detect whether the vessel is a vessel or not. So correctly detect that a vessel is a vessel. So basically, if you look at that, as the age advances towards 80, right, the sensitivity will drop dramatically, 0.1. So using the gradient, I think by for every 10 years, it will increase. Increase of age, it will decrease by 0.4633%. The sensitivity. Okay, maybe from our observation, I think maybe it's because of the poor contrast between the vessel and the background. Because as you get older, we cannot differentiate between your vessel and also the fiber artifacts from your retina. So that's the problem, I think. We think. Okay, and then we have another interesting result over here for the specificity. Okay, it will decrease. Okay, as the year decrease. So it means that if you're getting younger, okay, the specificity will decrease. So what do you mean by specificity? It will measure, okay, the ability of the classifier, I mean your deep learning, okay, to classify correctly the background, the non-vessel. So it means that if it detects a non-vessel, it will say that it is a non-vessel. It will not say that it's a vessel. So that's what it means. So it means it can detect the artificial fiber of your retina. Okay, if you see here, as the year decrease for every 10 years, it will decrease, the specificity will decrease by 0.05343%. Because we think, well, as you are younger, is because the characteristic of your vessel and also your retina fiber is almost the same. So it's difficult to distinguish because you are too young, it's too elastic, I think. Okay, this is the solution. Okay, basically what do we mean by solution? Because previously we used a hard classification, maybe to reduce this particular problem in terms of the specificity for the old ages. I think we can use like a soft grayscale. So basically what do you mean by that? We are using a softmax. So the probability distribution will have to determine multiple output, multiple classification, not just basically whether it's a vessel or non-vessel. There's nothing in between. So when we did that, okay, if you see the picture in the middle, at the bottom there, we can still see the vein, I mean the vessel, but it's very light in color. Compare to our previous result, whereby it will be classified as a non-vessel. So that is an improvement over when we change into soft classification. Okay, if we look at the specificity for the young age group, so we still have a problem, although we have changed to a soft classification, because the result is almost the same. We can still see the it will still classify the fiber, the artificial artifact on your retina. If you see the original image, if you see that cloudy white patch on your retina, that is what we mean by actually it's just an fiber artifact of your retina, but it will be classified as a vessel over here on the next two pictures on the rightmost, even in the middle. So it's almost the same. So I think we need a better features in order for us to better get the specificity higher for young age group. Okay, in order for us to do that, actually, I think we need to introduce a different kind of feature. So basically, we have research. Actually, there is a new innovation they call convolutional layer. Instead of you finding out what are the best features to be fed into your neural network. So with this convolutional layer, okay, it will automatically detect the best features for you. So let's look at an example of what do you mean by convolutional layers. Okay, if you see the picture on the left over here, okay, it is an X, right? So whenever the picture is distorted, okay, whether it's rotated, shifted, right? So basically, the neural network might not classify it, okay, as an X. So that's the problem, because the quality of the image, if you change it into a different angle, so the accuracy of our neural network will drop. So is it an X or is it not an X? So that's why. So basically, we're going to attach this convolution layer in front. Okay, after the image have been fed. Okay, before you go to your connected layers that I have shown you previously. So before that, there's some more layers. Especially is actually is this one. We're going to introduce convolutional layer. So these are very important because in our next project, we're going to use this. Okay, so basically the idea is that we're going to break these images into pieces. So basically the body, okay, is highlighted in the orange box. Okay, and then we have the arm and the leg. The arm is highlighted in the green box and the leg is highlighted in the purple box, right? So basically when you break them out and then you piece them back together, assemble them, then you will still get the same image. So this is the main idea of a convolutional layer. Okay, let's look closely of what actually the operation of this layer. So basically, this is your image, for example, 5 by 5. So this is your image, 5 by 5 image, and then we have a filter. The filter, the responsibility of the filter is to find out, okay, whether you have that X shape within your image. So how do we do that? So we have to patch the filter into the image, and then we have to slide it over and apply some element-wise multiplication. Okay, let's try to do that. So basically, if we patch this filter, okay, into the top left corner of your image, so and then you apply this element-wise multiplication. So 1 times 1 plus 1 times 0 plus 1 times 1 plus 0 times 0 plus 1 plus times 1 and plus 1 times 0 plus 0 times 1 and plus 0 times 0 and plus 1 times 1. So basically at the end, yeah, what you will get is number 4. So that is your new features. They call it feature map, right? So basically we have to do it, okay, over the entire image. So there is only one patch. So we need to slide over the filter, for example here, in the middle, okay, by 1 stride. Okay, so basically we do that again, the same process again, and we get number 3, right? Okay, and then we have to shift again to the end of the picture, so top right, and then we repeat the process until we get this feature map, and then you go to the bottom and then you strike 1 until to the right, okay, until you finish, then you start over again at the bottom until the end. I hope you understand what is the idea. So basically at the end, if you see this 444 diagonal, so the shape is almost like an X. So this is the new feature map. So this is what the convolutional layer will do. So basically it will extract those features, okay, although they are tilted, the angle shifted, and then it will maintain the spatial information. So before this, if you still remember the connected, functional connected layer, all the images will be transformed into one metric, right? It's like 1D tensor. So basically, all the information about the spatial information will be gone. So that's why, okay, to conserve that, convolutional layer is the best approach. Okay, so this is our project, okay, whereby we use this convolutional neural network. Okay, so before that, some of the background into our project. This was, I think, in 2020, we did this project. And then we have a limited number of publicly available COVID-19 chest X-ray because it's not available. It's not easy to get, right? It's not easy to get. Okay, so basically, what we did, okay, because again, just to remind you, when we have a limited number of images to train, so limited number of data to train, our architecture, okay, network will be questionable. So it means the accuracy, okay, will be questionable. How reliable is the result? So, okay, if you have any question, you can ask, no problem. Okay, so basically, what we did was, okay, we find similarities, okay, into the publicly available chest X-ray that are available from NIH, National Institute of Health. So basically, they have a lot of X-ray images. Okay, what are the common between these images is that the ground glass opacities that they are detected. So almost all the COVID-19 cases, 50 to 60% of it, they found this ground glass opacity. What do we mean by that? If you see on the picture over here, this like glassy white translucent image there. So basically that is what we mean by ground glassy opacity. So it's similar to the images that we find from NIH. So I think we can use these images to train. After that, we use the real data to test. So this is our basic idea. So this is our methodology. So the chest X-ray for NIH, okay, they have classified it into, label it into 14 lung diseases. For example, pneumothorax, collapse of your lung, and then fractured, and then cancer, mass nodule. Okay, and then the other one that are most important that we wanted to use was this A-space opacity. So we extract that. So basically, from this particular data set, NIH, we have 112,120 images. So from that, we only take 4,376. Okay, what Google did was very interesting. Google Health, they reviewed the ground truth. They reviewed the label for the diseases. Okay, this time they wanted more accuracy in terms of the label. So they get between 3 to 5 experts to review this particular X-ray images and then determine what are the disease. So at least they have 3 for each image. So it is more accurate. We can say that's how we use it for our study over here from Google Health. So you can just go to the, what do you call it, the form, fill those in, and then they will give you all those information. Okay, so we found that from the 4,376, 2,166 is with opacity, and the rest is without opacity. And then we divide it into training set and also validation set. For training set, we take 70%, if I'm not mistaken, and for the validation set, we just take the 30%. So why do we have to divide training set into the validation set? So that we need to know when to stop our to test our hyperparameter when to stop, okay, because the data will get overfitted. So that's why we know exactly when to stop with this validation set. And then our hyperparameter was optimized. Okay, so for the testing, okay, we are using this COVID chest X-ray data set from University of Montreal. I think it's available from the GitHub. Okay, it was very small amount in numbers, 154. And then we use all of them, 154, because we don't have enough. And then according to the prevalence rate, the COVID cases was like 3% or 2.5%. So that's why, according to that, we take only 5,828 from the chest X-ray for no finding, because to reflect that prevalence rate that we are having COVID at that particular point in time. Okay, so for our project, remember that we are using the convolutional neural network, okay, with 101 layers. They are called ResNet. Okay, from the background, I think you are familiar now what is ResNet. So basically, we freeze the whole entire CNN for the ResNet, 101 layers, so that because they are already pre-trained on the ImageNet. Remember ImageNet of 1 million images, so it's already, we can consider that their weightage are optimized. So what we did was just to introduce a new fully connected layers so that we can customize our neural network, okay, to classify COVID cases with non-COVID cases when we viewed those X-ray images. Okay, and then it will be the probability will be calculated with the softmax that we have mentioned earlier. And then the new classification output, we just use the loss cross entropy. Okay, it's just summation of negative log, natural log. I think natural log, and then your probability for those class that one, not zero. Okay, so now looking at the results, looking at your UC curve. So basically, it was 0.82, which is okay if we compared with the random coincidence. The blue line is random coincidence. It means that 50-50 chance without having this neural network to do the prediction. So you have 50-50 chance, right? So it's much better than that. But if we compare with the other systems that we have read through the journals, ours is not that good compared to them. They are like 0.9 something. So I think that is because, okay, that is because the modality that they have used is much better than what we have used. So basically, we are using X-ray images. They are using CT scan. So it's like 3D images. So it is much better. Okay, and they are with a higher resolution. And then they are using very small data. That's the problem. They use a very small data set. And because the overfitting, we assume that that's why they get a better results. And then they are using the data from the same machine. At least if they use for the testing case with a different machine, then it's better, I think. So it is more biased. This is what we think. I don't know what you think. Okay. So looking at the confusion matrix for the output class is the ground truth that we have gotten from the data set. Okay, and then this is the target class, meaning that this is what our neural network did predict, right? So basically, if you look at that, the sensitivity is 77.3%. So basically, these are the true positive. So basically, on the green square here, right, at the bottom right. So basically, this is when it is COVID, and then our system also said that it is COVID. And the accuracy is the combination of the true positive and also the true negative, and it is accumulated up to 71.9%. So it's quite okay, because we don't have all the images from COVID. If we have that, I think the result would have been better, right? So let's look at an example of a true positive and a false negative. So this is an example of X-ray images with a true positive. And then how about the false negative, false positive, right? These are the images with a false positive. So do you find any differences between them? Okay, so in order for us to seek, okay, to find out, okay, which part of the features are actually important for us to classify it as COVID or not. So we use this gradient weightage class activation mapping. The algorithm was already established. We can just apply it. So basically, what does it do? So it will determine first, okay, once you go to your forward feed, it will calculate the gradient score. So the final gradient score, this is what we wanted. Okay, and then we track back, okay, and find okay, so basically with this final score, what are the features, okay, that are very important. So we have this heat map. So the one with the bright red, meaning that these are the important features that will determine whether it is COVID or not. So the one that are yellow is not as important as the one that are red, but still as important, but not the one that are blue. They are not important. So basically, once we zoom in, we find out that these features are actually somewhere in the right mid-lung zone. So this actually confirm what the radiologists say, that usually COVID patient, they have this patchy consolidation. Consolidation meaning that there's a liquid, okay, that accumulated on their right mid-lung zone. Okay, so so that was our two projects that I think worth mentioning. Now, this particular deep learning is not without limitation. One of the most problematic thing about it is what we call by catastrophic forgetting phenomenon. What is this, right? So let's have an example so that we can understand this particular phenomenon. Okay, so let's say we have a neural network, deep learning, and then we wanted to classify. Our first task is to classify whether it's a cat or a dog. Okay, basically, very simple classification. Okay, and then if we use the same network, okay, to classify a bus or a car, is it a bus or a car? Then it will forget whatever you have learned before. That's the problem with this neural network. So it will start over and it will reweight all the connection again. Okay, and then it will tend to identify bus and car with higher accuracy, but not cat and dog. It will forget everything about cat and dog. So if you wanted to classify that, then the accuracy will be very, very low. That is the problem with this neural network. Okay, so what are the solution, right? So basically, we have one simplistic approach. It's just to train each task, for example, to classify dog and cat in silo. Okay, and then we use a different neural network to classify car and bus, and then we save all the weight. So whenever we wanted to do some prediction to categorize, so we choose the right one. We choose the right weightage. So it will not be scalable. We have a problem with choosing the right one, and then every time you have a new task, you will have to come up with a new network. So alternatively, we have a very elegant approach here. They call elastic weight consolidation. Okay, so what is elastic weight consolidation? So basically, don't worry, we're going to finish very soon. Okay, I will not take a lot of your time. Don't worry. Okay, so basically, okay, if you look at the first figure over there with all the orange connection. So basically, whenever you have classified a cat and a dog, okay, so those are the most important connection that will be activated, okay, based on the features of the dog and the cat. Like for example, the ears, the long ears of the cat, okay, and then these are the important connection, and then we freeze it. Okay, so now, okay, when we wanted to classify the dog and also the bus and also the car, we use the same network, but we have frozen the previous learning, the weightage from the previous learning, and then we just apply it on top of the previous network, and then this blue connection that are the one that are important for the activation of the bus and the car. So basically, we keep going on doing this. So when we learn the second task, it will also use the weightage that we have learned from the dog and the cat. So basically, it will learn also from the previous task. So it means that the second task will learn also from the previous task. So this is good. This is actually how human are learning. So basically, when we are like a baby and a toddler, so basically it's easier for us to learn new things, right? And then we keep on adding up new things to learn new knowledge. So as we grow older, okay, you find that it's very difficult to learn because the elasticity, okay, of your neural network, okay, have been what do you call it, concentrated, so there's difficult to find new path. So it mirrors, okay, usually it mirrors how the human works. So now they are moving toward this, okay, to address the catastrophic forgetting. Okay, so what are the implications of the neural network? So if you look at from the data from the ImageNet, okay, so the extrapolate according to the percentage error. So if you need more computation operation, they call it floating point of operation. So if you need more computation, right, you will reduce the error that you will get from your neural network. So it will become more perfect, better than human. Okay, but the problem is, okay, it will emit a lot of carbon dioxide emission in pounds. Okay, so if you look if you just reach 5%, it is as though that you are generated, the CO2 that you are generating is like the one that you generated in the New York City in a month. So it's quite a huge pollution, right, to the global warming. So this is the implication of neural network. So maybe we need a different approach, okay, of doing this training. Okay, we are hunger for this computational power. Okay, so we need to find a different or more what do you call it, optimal approach, right? Not to just to run through everything and then try to find what is the optimum weight. It's impossible, right? And then you crunch all the data that you have as much as possible just to reduce the error. Okay, so the current idea to reduce this, wait, I need my power. Sorry, I need my, my laptop is out of power. Okay, so basically, so how can we reduce? Okay, the most simplistic approach is just to prune, okay, all those unimportant connection that you will calculate for the radian. So this is the most simplistic approach. So they have found a most elegant approach. So basically, actually, what was done before, every time you have you do your computation, so you will have to extract those data from the memory into the CPU. And then after the next iteration, you have to take another set of batch of data into the CPU. So basically, because of this moving of data from the external memory into the CPU or GPU, basically use a lot of the energy. So what they propose is to do this computation on the memory itself. So you don't have to move between the CPU and the GPU and the memory. So within the memory itself, these are the architecture that they have showed. They call it analog AI. So basically they are using Ohm's law. It's all electrical, right? So basically they just sum, okay, all of this input that are already there on the memory, okay, with this weightage that are in the horizontal blue line, if you see, and then you will get the result to the next stage. Okay, so basically these are the new idea. They are now looking into this, whether it's feasible or not. They're trying to find out with experimentation. Okay, so what are the way forward? So basically, the idea, okay, is to build a system with a conscious. That is the real idea of AI, artificial intelligence, right? But the problem is it's not that easy. If we keep on debating what is consciousness, we never move forward, right? Always debate and debate and not moving. So what is the practical view of this consciousness? So it's actually the ability, from our point of view, is the ability to think about the future, not to debate into the higher level thing, right? Just the ability. If a cat, okay, let's say a cat can plan for the next 10 years what they're going to do, that is what we call consciousness. Usually human can do this very well, but not animals, right? And it's not easy to get to this stage where you can have a cat or even a robot, a system with the ability, okay, to think about his own future, right? And then emotion is of course very far away to achieve. What we are focusing actually should be on the general intelligence. So what we mean by general intelligence, not thinking too far ahead, what we can achieve in the near future. So basically, let me look at the time first. MashaAllah, it's running. Okay, I'm going to finalize this. So basically, is the ability, okay, whatever we have learned from the first task, we can apply it, okay, on a different task. So this is what we call general intelligence. So for example, if you take a cat, okay, you put it in the field somewhere, okay, that particular cat can survive on its own. If you put in the forest, it can survive on its own. But if you put a robot in the field and then you move it to a different environment, the robot might not survive if you put in the forest with a hilly slope. This is what we're trying to achieve in the near future. So basically, just a simple intelligence. So it means that you can just apply whatever you have learned before. For example, a robot. So when it pick up something, let's say a square shaped item, okay, it can pick it up. So when it pick up a round shaped item, it might drop it. So it cannot use what it learns from before. Maybe try to adapt to also pick up a round object. Okay, so if you look at a baby, okay, a baby doesn't even have to need a huge amount of data, okay, for it to learn. Okay, basically baby, whatever this baby have observed, okay, it will create a mental model, okay, on how the thing works. So basically when it interact with it, okay, touch it, there's a feedback that it will change its mental model. Okay, and then with a few iteration, that this particular baby will find the right understanding of the phenomenon to draw a certain conclusion. So it knows what is happening. So it does not need a lot of computation to converge the model to get into an optimum weight, right? So the baby is much cleverer. Okay, so thank you very much for listening and taking your time for this particular talk. It was a very good time to share. It's at the end of the year. Okay, so thank you very much. I pass it back to our Dr. Rafiez, right? Rafiez.
Okay, thank you very much, Dr. Izzuddin, for the interesting and fruitful information in this session. Okay, everyone, before we end the session, we just go for a quick Q&A session, yeah? All right, so I just would like to ask, is there anyone who would like to point out any questions related to AI in healthcare? Or any projects that Dr. Izzuddin or our team have completed together? All right. So I think we just go to a few simple questions. Yeah. All right.
Okay.
Actually, there are a few questions that I managed to find out. All right, about AI in healthcare, which is when is the time that we should use AI in healthcare?
Now.
All right. So if we say it's now, right? So basically, what will be the patient's privacy? Who will protect the patient's privacy?
Masya Allah, very good question. Okay, about patient privacy. Now we are doing another project. Basically, remember the convolutional neural network, right? So basically, we pass through the data. So then we're going to, what do you call it? Extract the important features. After that, we're going to minimize our the amount of data that we have. So once we gone through this, so all the data and all of those information that we have from the patient is gone because it just have been transformed to the features. So we are currently doing this project. We are trying to get it published. We are waiting for the editor to approve. So after that, we use a supervised instead of sorry, unsupervised. So before this, everything is supervised, right? Everything have a ground truth, have a label. So we change it to unsupervised. I think this is a much more better methods. So we don't need too much data. So the problem is actually with data. When there is too much data, so we need to change the way that we do stuff, I think. And then the accuracy that we found is almost similar to with supervised data. So once it's published, then only we can talk more about it, and maybe you can read it. Because otherwise, because it's not published yet, right? Okay. Okay. Any other question?
All right. Okay, thank you, Doctor. Another question from Dr. Rokia.
Uh,
Very useful and interesting research. So how do you plan to apply the technology in hospitals in Malaysia?
okay. Actually, we have what do you call this? We have already we have gotten the grant for PRGS for Petirigium. Basically, we have developed a system. So we are promoting our system now into the hospital. Maybe it can help our eye specialists. Okay, as just as a like a system that can support them to make decision. Basically, we nearly finished it. So the system is already there. And we're going to close PRGS very soon because yeah, we have a lot of reminders to close it. Inshallah. So basically, we are talking to hospitals now on how they can use our prototype.
Okay, thank you very much, Dr. Izzuddin. All right. Is there any other questions? If not, we are going to end the session. Yeah.
Dr.
All
Rafiez,
right. So
Dr. Rafiez,
okay.
yes,
Yeah.
I just have a quick question. Sorry, this is not my area, Dr. Izzuddin, and indeed, it is very interesting, indeed, and inspiring. So I just asked a few questions that I know, but of course, this is not my area.
No problem.
So, I saw that you mentioned about the freezing, I mean the frozen layer, right? Then normally we have the transfer learning.
Transfer learning, yeah.
Yeah, we have the bottleneck, right? Bottleneck. Yeah. So now, how many experiments you have to work on for the COVID-19 before you can go for the fine tuning parameters? So how many experiments on average? Thank you.
All right. Okay, I think it's trial and error. So basically now more data are coming up for the COVID X-ray images. I think if we use more, and then because the hyperparameter is like an art and science. So basically there's no like formula which is the best parameter. So you also have to use art. Maybe we have like crowdsourcing to find out how people have done it. So what are the popular parameters that I've used? Maybe we can try with that first, and then maybe we tweak it and then find what are the best parameters to use. So now a lot of data have been published, so maybe we can use that, because these are only the preliminary result. So maybe we can, later, inshallah. Inshallah.
Okay, thank you. All right, we have another question from Brother Jamal. I hope
Okay, no problem.
Okay, Brother Jamal, your comment in consciousness is interesting. Can you elaborate more on the consciousness?
Okay, consciousness, it's not an easy thing. Even I don't understand consciousness. That's why I take just a pragmatic approach of consciousness. So basically, if someone or something that can plan for the future, I think that is consciousness, more practical proof. But I don't know whether it's right or wrong. Maybe I'm wrong. but if you look at the philosophy of consciousness, if you look at the religious perspective, Islamic perspective, it's like huge area. So I'm afraid to go to that level because it's too complicated. So that's why I just take a pragmatic approach to AI, and forget about the debate. I don't know whether I'm right or I'm wrong to do that, because we are academician, we should pursue that, right? But I think for ethics, let's say you apply AI in a robot because they might harm you, right? So maybe we can just come up with some kind of a protocol. So the higher level protocol, okay, will govern the lower level protocol. The lower level protocol is basically your neural network, right? What you're going to do, and then it will be guided by the higher level protocol to see whether are you going to harm human if you take this action. So that is very important to control the robot, because neural network, once you apply it into not a specific context, so to another completely different context, we don't know how it will behave. That's a problem with machine learning, I think. So that's why it's actually a black box. That's what people are saying about it. So maybe you can take that approach. So basically we can control it somehow with protocol architecture. This is what I'm thinking. I don't know.
Assalamualaikum warahmatullahi wabarakatuh. Can I have
MashaAllah.
Okay, you mentioned the word consciousness. I thought you want to talk about conscience. You know, there's two things here. Conscience is like what is right, what is wrong, value, etc. Right? So that's why, of course, nowadays you see in the movies they try to see how the robots were trying to make decision whether to harm or to protect. Meaning there's some training of making decision and putting values there. So is it just for the movies, or are we having that in real stuff?
Even in real life, I think they are still debating what is consciousness, even up to that level. So they have not concluded yet. Actually, what do you mean by consciousness? The definition of consciousness. So yeah, that's why. Okay. The other thing for me is that maybe we can apply. For me, it's just to control the uncertainty, either through the protocol or give the machine more rigid information. For example, you combine between neural network and also symbolic AI. Remember, I talked about symbolic AI in the very first slide. So basically, because symbolic AI is concrete. Okay, I give you an example. Autonomous car, right? Autonomous car. So based on the radar, okay, they will make decision. There's an actuator whether they are going to move to the right or to the left or move forward, or whether to stop if there's like pedestrian or something. So basically, they will also support those decisions with a GPS and also the map of the surrounding. So that's how they make better decision. So I think that's the for me, about consciousness is up to that for me, but actually it's more complex than that. Yeah, so it's too complex for me to take into that direction. So I just take a simplistic approach to it. So as long as we just have a very general intelligence, I think it's good enough. At least we have moved one step forward for me, and not go deep into the debate. That's my stance. I don't know whether I'm right or I'm wrong.
Okay, thank you very much.
Okay, thank you.
Thank you very much, Izzuddin. Okay, everyone. So I hope there is no more questions. So I would like to thank you, Dr. Izzuddin. Inshallah, we are looking forward to having you again in the future.
Inshallah.
And thank you very much, everyone, to the organizer, Office of Responsible Research and Innovation, KICT Promotion and Marketing Team, for organizing this webinar. And thank you, everyone, for your participation in this webinar. So we hope to see you again next time, inshallah. So let's end our session with Tasbih Kifara and Surah Al-As. Okay, everyone. So thank you very much for joining this session. So hope we can see each other soon. Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam warahmatullahi wabarakatuh.